Today's lecture talks about moment of inertia of diatomic molecule. Moment of inertia of diatomic molecule. What is meant by diatomic molecule? Diatomic molecule means two atoms combine to each other. Suppose we take example of AB diatomic molecule. A atom, this is A atom, and this is B atom. Any atom having some mass, A atom having mass m1 and B atom having mass m2. Then R0 is the internuclear axis or bond link between two these atoms. Z is the center of gravity. Atom A and B rotate about its axis through center of gravity. R1 is the distance between atom A and center of gravity. R2 is the distance between atom B and center of gravity. Then we know that center of gravity balance to this atom A and atom B. M1 R1 is equal to M2 R2. We know that R0 is equal to R1 plus R2. Putting the values of R2 in this equation 1, we get M1 R1 is equal to M2 R2 value, which is the R2 value. R2 is equal to R0 minus R1. R0 minus R1. Solve this bracket. M2 R0 minus M2 R1. M1 R1 is equal to M2 R0 minus M2 R1. This minus term go to this side. Then we get M1 R1 plus M2 R1 is equal to M2 R0. Common term R1 is equal to R1 common to this term M1 plus M2 is equal to M2 R0. Then how to calculate this R1 value? R1 is equal to M2 R0 divided by M1 plus M2. We are easily getting this R1 value. Similar procedure done, then we get R2 is equal to M1 R0 divided by M1 plus M2. This is equation 2, this is equation 3. Then after that, we know that moment of inertia I is equal to M1 R1 square plus M2 R2 square. In this equation 4, put up the values of R1 and R2 from equation 2 and 3. We get M1 R1 value M2 R0 divided by M1 plus M2 bracket square plus M2 R2 value M1 R0 divided by M1 plus M2 bracket square. Solve this bracket. M1 M2 square R0 square divided by M1 plus M2 bracket square plus M2 M1 square R0 square divided by M1 plus M2 bracket square. We are easily observed that these two terms denominator is same. then we write one denominator of this term, m1 plus m2 bracket square. We are write this term m1 m2 square r0 square plus m2 m1 square r0 square. We observe this term, we are easily common to the m1 m2 and r0. Then we get m1 m2 r0 square. Common this term from these two terms. Then we get m2 plus m1 divided by m1 plus m2 bracket square. Cancel this word term and we get m1 m2 r0 square divided by m1 plus m2. We know that reduced mass is nothing but mu is equal to m1 into m2 divided by m1 plus m2. Putting this value in equation, we get I is equal to mu r0 square. This is a formula of moment of inertia for diatomic rigid rotor. We are easily getting this point. Then after that, rotational spectra of diatomic molecule. Rotational spectra of diatomic molecule. How to calculate rotational spectra of diatomic molecule? Rotational spectra. In rotational spectra, delta J is equal to plus minus 1. Selection rule of rotational spectra, delta J is equal to plus minus 1. Which transition is allowed? Which transition is forbidden? Delta J is equal to 0, J is equal to 1, J is equal to 2, J is equal to 3, J is equal to 4. These are the few rotational energy level. But out of this energy level, only delta J is equal to plus 1 energy level are allowed transition. In this selection rule, absorption spectra and emission spectra, these two spectra are considered. Which is absorption spectra and which is emission spectra? Absorption spectra means molecule absorbs some energy in lower state or ground state, then it goes to the higher excited state. This is the absorption spectra. This is the absorption spectra. Delta J is equal to plus 1. And emission spectra, phase molecule already present in excited state and they goes to the ground state. It means the excitation of energy. Then we get emission spectra. Delta J is equal to minus 1. But in rotational spectra, we are discuss about only rotational absorption spectra, means delta J is equal to plus 1 selection rule. J is equal to 0 to 1, this is allowed transition. J is equal to 1, 2, J is equal to 2, this is allowed transition. J is equal to 2 to J is equal to 3, this is allowed transition. J is equal to 3 to J is equal to 4, this is allowed transition. But J is equal to 0 to J is equal to 2, this is forbidden transition, because this transition is not allowed, or this transition is not allowed because it breaks the selection rule of rotational spectra. Delta J is equal to plus 1. Transition to the nearest one, higher one. J is equal to 0 to J is equal to 1. This is the plus 1 change. Change in transition is plus 1. J is equal to 0 to J is equal to 2. Change is plus 1. Change is plus 1. In this transition, change is plus 1. Only change is plus 1, then transition possible in rotational spectra. Otherwise, transition is forbidden or not possible. Then after that, energy of rotational spectra. Energy of rotational spectra. Energy of rotational spectra. Energy of rotational spectra is equal to h square 8 pi square I j plus 1. According to Schrodinger wave equation, to solve the Schrodinger wave equation, then we obtain energy of rotational spectra E is equal to h square 8 pi square I j plus 1. Then rotational energy is equal to h square 8 pi square IC j plus 1. This is the rotational energy. C is the velocity of light, h is a Planck constant, j is a rotational constant. But this term is nothing but b. B means rotational constant. H square 8 pi square IC is a B. B means rotational constant. Then we get x1 j is equal to B j plus 1. This is the equation of energy of rotational spectra. Then use of this equation, or how to calculate line. First line, number of line, then transition, then position of line. How to calculate position of line? Which transition occurred? Which line? First line, second line, third line. This is the line. How to get in first line of which transition and which position? Mu bar is equal to 0. Which transition getting this line? Transition epsilon 0, epsilon 1, epsilon 0 to epsilon 1. Epsilon 0 to epsilon 1. How to getting this line? Epsilon 1, j is equal to 0. J is equal to 0 means putting this value in this equation 0, 0 plus 1. 0 plus 1 means 1. But multiply this 0, we getting all this value is 0. First line is mu bar is equal to 0. Second transition epsilon 1 to epsilon 2 transition. In this transition, putting the j value 1, then we get j is equal to 1, epsilon j is equal to b 1 plus 1 means twice b. Mu 1 bar is equal to twice b. Then after that, next transition epsilon 2 to epsilon 3. J, putting the value j is equal to 2 means epsilon j is equal to b 2 plus 1, we get it 6b. Epsilon 2, sorry, P2 bar is equal to 6b. We are clearly observed that first line, this is the first line. Which transition observed first line, epsilon 0 to epsilon 1. We get it first line. Then position of line, mu bar is equal to 0. Then next second line, which transition occurred, epsilon 1 to epsilon 2. Position of line, epsilon 1 bar is equal to twice b. Then third line, epsilon 2 to epsilon 3, value is 6b. These are the number of line, transition and position of line in rotational spectrum. Then next point is spacing. Rotational line are equispaced. Rotational line are equispaced. Means 0, twice b, 4b, 6b, 8b. Means it is clear that rotational line are equispaced between distance twice b. How it is possible? Because these transitions are spacing distance between twice b. Spacing distance between twice b. Twice b, 4b, 6b, 8b. Then after that, next point is we are calculating energy difference. Delta E is equal to EJ minus EJ dash, means higher line energy minus lower line energy. We have obtained this delta E value. Then microwave spectroscopy or rotational spectroscopy, application of microwave spectroscopy or rotational spectroscopy. Application of microwave spectroscopy. First application is calculating of moment of inertia. Calculating of moment of inertia. Second application is calculating bond length. Calculating bond length of diatomic molecule. Diatomic molecule. How to calculate moment of inertia of diatomic molecule? We know that I is equal to mu r0 square. This is the moment of inertia. Calculating of moment of inertia. Then how to calculate bond length? I is equal to mu r0 square. Mu is nothing r0 square is equal to I divided by mu, means r0 is equal to I by mu. Then we are easily calculating bond length or internuclear distance from this formula. Then after that, vibrational spectroscopy. Vibrational spectroscopy of diatomic molecule. Vibrational spectroscopy of diatomic molecule. Vibrational spectroscopy observed in IR region. Vibrational spectroscopy observed in IR region. And next concept observed in this vibrational spectroscopy, that is 0 point energy. What is meant by 0 point energy? On the x-axis, energy will be plotted. Then vibration quantum number, is equal to 0, P is equal to 0, P is equal to 1, P is equal to 2, P is equal to 3, P is equal to 4, P is equal to 4. Then energy is equal to half h nu, then 3 by 2 h nu, 5 by 2 h nu, 7 by 2 h nu, 9 by 2 h nu. Or in another sense, E is equal to P plus half h nu. In another sense, energy can be written in the form E is equal to P plus half h nu. Okay, getting this point? Or first, energy is equal to half h nu. This is the formula using for calculating the vibrational energy of diatomic molecule. E is equal to V plus half h nu. Phi is equal to 0. Phi term indicate vibrational quantum number. First, vibrational level, phi value is 0. If phi value is 0, then putting this value in equation, 0 plus half h nu. Then we get half h nu. Means if vibrational quantum number value is 0, then their energy of the diatomic molecule is 0 or something, no 0, because molecule in any molecule present at rest position, but their energy is not 0. Why their energy is not 0? Because the molecule are vibration state. They are smaller vibration. They are in molecule. There is a small vibration present in the molecule. They are not at rest in position. Due to this small vibration, they are getting this some amount of energy. E is equal to half h nu. Then vibrational quantum number value is 1. Then vibrational energy is 3 by 2 h nu. If vibrational energy quantum number value 2, then we getting energy value is 5 by 2 h nu. If vibrational quantum number value 3, then 7 by 2 h nu. Vibrational quantum number value 4, then we getting 9 by 2 h nu energy. 0 point energy means if molecule present at rest position, vibrational quantum number 0 value, then we getting some value. Some means half h nu is called 0 point energy. Then next point is a selection of vibrational spectroscopy. Selection rule of vibrational spectroscopy. Vibrational spectroscopy. Delta P is equal to plus minus 1. Selection rule for vibrational spectroscopy, delta P is equal to plus minus 1. Means this transition is possible. This is allowed transition. This is allowed transition. This is allowed transition. Why this is allowed transition? Because these are the various vibrational energy level, but changes plus 1. P0 to V1 changes plus 1. P1 to V2 only changes plus 1. That's why these are the allowed transition. But transition from V0 to V2, this is forbidden transition because changes plus 2. Then absorption spectra, absorption vibrational spectra, absorption vibrational spectra and emission vibrational spectra. Emission vibrational spectra. What is the difference between these two spectra? I already explained in rotational spectra. Absorption vibrational spectra means energy of molecule. Molecule absorbs some amount of energy and it goes to the higher energy level, this is the absorption spectra. This is the absorption vibrational spectra. And if higher, transition from higher to lower, if molecule present at excited state, then it return or it emits some energy, it return to the ground, then we getting emission spectra. Emission vibrational spectra. But selection rule for absorption spectra, delta V is equal to +1. Selection rule for emission spectra, delta V is equal to -1. But more focus on this in diatomic vibrational spectroscopy. More focus on this absorption vibrational spectroscopy, not for emission vibrational spectroscopy, because molecule absorbs some energy and it goes to the higher excited state. That's why absorption vibrational spectra is more important than emission spectroscopy. Then after that, some numerical in your textbook were easily solved by using this formula, energy of rotational spectroscopy and bond length. Then after that, Raman spectroscopy. What is Raman spectroscopy? Raman spectroscopy is mutually exclusive to IR spectroscopy. Raman spectroscopy, if molecule polarization